Hello everyone. So in the previous lecture we did completed the derivation for SVM, and if we see it, what approach we have performed. You got a 2D data. This is your 2D data. I can have F1 and F2 as two features. We do have classes, class A, class B, and what we require is to divide these classes. So we want to make a decision boundary that we are calling as hyperplane, and that we want to be as optimal. For that we need help, and help we are taking from the data points which we need to identify what these data points will be, so that with the help of them I can make as class boundary of B. This will become class boundary of A, and the width, the distance between the class boundaries, I am going to say as margin, and everything depends on this only. Okay, you did maths, and in maths we want max margin, but as we know there are two types of margin: hard and soft. Yesterday only I did explain this point. Hard margin is a clear separation between the classes. Soft margin, okay, we do compromise, we do have errors, and anyhow, we see how to manage these errors so that it should not increase. So, with short margin, we are expecting not to have overfitting, because here there is a chance of overfitting. Okay, here we are trying to avoid that. The equation for the margin and all the things which we did, your margin was 2 by W, and then for margin to max we want W to min. So we created an objective function named as W square by 2, and we do have a constraint equation that was given as y wx plus b minus 1 greater than equal to 0. That was our constraint equation. So we want to solve this thing under this constraint, and in this solution we seen theorems, approaches, how it can be solved. How this problem, this optimization problem, can be solved? For that, you followed first Lagrange. Okay, Lagrange's theorem, where you are having a multiplier, which you are calling it as lambda. And what you used here was f minus lambda g equal to L. And you want this dl by dw, dl by db, dl by d lambda. You put all of them equal to 0 to identify the value of x, y, and lambda. Lambda, you told, sir, as per explanation, multiplier, which is to balance the trade off between objective function and the constraint. Because obviously, this objective function change will put a change over this constraint, will put a change over the objective function. So, how much change we do expect in an objective function? I need to balance that, I need to control that. So it's just like as regularization, okay, to control the impact of constraint over the objective function. We do have many multipliers because your equation will be like w square by 2 minus lambda yi w xi plus b. This is lambda I minus 1. This is what your L is. So for that, you do have KKT and SMO. These two things also you covered. KKT talks about Lagrange only. These are the rules which define conditions to solve an optimization problem which is under constraint. Okay, without constraint, that's an easy task. We don't have to put so much effort related to that. It's directly differentiation, putting to zero, you'll get the result, because we need to perform only maxima and minima. Okay, fine. So that's easy. Unconstrained is having an issue. So KKT defined the rules, conditions. Okay, you should have an objective function, you should have a constraint, you should have a primal problem, you should have a dual problem. So primal problem was our initial problem. Dual problem, if we are unable to solve a primal problem, then we have to go ahead with the dual problem. And in dual problem, what we did yesterday is, what we got the result in the primal problem, we resubstituted. Okay, we resubstituted that into the equation. Same equation, same constraint equation, same optimization equation. Okay, we have put that. Okay, and after putting, we haven't done any differentiation. In primal, we did the differentiation. In dual, we substituted the value in the optimization problem and converted it into dual problem, and whatever be the combinations were made with it, and we got some equation. And then on the basis of that equation, we found the value of lambda and w, and by them we found the value of b. So with KKT, SMO was also used, where it has been told, okay, take divide a problem into sub problem. You are having a big problem, so sequential optimization techniques. Okay, so in this particular case, what you did is you have to divide a problem into sub problem, like take alpha 1, alpha 2 as your lambda values, keep rest as constant. Okay, that's what we did. Okay, and yeah, we did solve this particular thing, and that's the goal. Because once you got these parameters wb, okay, this wb defines the hyperplane wx plus b equal to 0. That is the equation of hyperplane. So how this hyperplane is going to be adjusted, that depends upon what? Support vectors. And for support vectors, you require this w, na? You require this w, what it should be. Okay, so we have done the entire solution of SVM. This maths is very much important. Okay, so initially we were dealing with the classification problem. Okay, SVM, we do start with classification, and the entire maths we did this for classification. However, I told that support vector machine can also perform regression. Okay, now the question is, sir, how it can perform the regression? Because the approach which you have told is we do have a hyperplane that can divide the data points into classes. So again we will be following a similar kind of approach to perform regression also, because the classification regression are different, sir. So what we are going to apply? Fine. Because if we talk about the algorithm, so algorithm support vector machine, that is the core. Initial approach will not change. Initial approach will remain same. The question is, okay, task now you have different. Previously you are doing classification, now you are talking about the regression. So let me share my entire screen now, and let's talk about how support vector machine can perform regression. Let me share my entire screen, and this is also interesting. Okay, fine. Now if you want to perform regression, we do have outcomes which are continuous in nature. Okay, continuous outcomes we require. But sir, in classification, sir, you are having discrete outcomes or categorical outcomes, sir. So they can be separated. How, sir, continuous we can separate, sir? Continuous can't be separated. So classification will fail here. But sir, algorithm is sir same, sir. Previously, we studied algorithm linear regression for regression, logistic for classification, sir. Both are different algorithms, sir. Here you are saying we are having same algorithm, but approach are different. How? See, let me tell you. Again, we are having the data distribution. Let us consider features F1 and F2. We are having data distribution. This is how, let us suppose, it's present. Now you want to look out for regression, those data points which will be my outcomes, continuous in nature. I can't make a hyperplane, but I can also deviate from my path of support vector machine, because the initial concept of support vector machine says that we require support vectors. So we require support vector for what? For what purpose? In building hyperplane? No, sir. Then what? For what purpose we require support vector? In regression, let me tell you one thing. In regression, they use a mind and told we have an epsilon tube in support vector regression. Okay, they made a line like this and told that this is epsilon tube. Previously, just we are having a line to classify. Now they are building a tube, and any point which is present here on the boundary of tube, they called them as support vector. Sir, same thing, sir. Sir, we have seen class boundary, sir. We have seen this thing, sir. Class A, class B, sir. Boundary data points you told us support vector, sir. In that particular case, this is, if any point, support vector. Support vector. Okay. So if these are the support vectors, we made not a hyperplane concept. We made, okay, this is a tube. We need to perform regression. So they told that any point which is present inside a tube, any point inside tube is our regression point. Any point which is present outside the tube will be considered as an error. Okay, so instead of just making and defining, okay, this is A, this is B, no. What they did is, still the approach is different, but they are trying to use the base of SVM. Here, this is above the line or the central line of my tube, and this is below the tube. Okay, below the tube, and obviously this is the margin or the width. So core concept of SVM doesn't change. Problem changed, regression. So they told, okay, regression, make a tube, and anything which is coming inside the tube is good. Anything which is coming outside the tube is error. So if a point is coming here, then it's an error, and it is represented by slack. This is slack 1. Any point, okay, here, this is slack 2. Okay, here, this is slack 1 dash star. So they are called as slack variables. SLACK, slack variables. Okay, so let me summarize because I am going to describe it more. Okay, I just been introduced this concept. In SVR, instead of hyperplane, we are having epsilon tube. And what is epsilon, sir? Sir, you're saying epsilon, epsilon. What is epsilon, sir? Epsilon is this distance. This distance, I am saying it as epsilon. Okay, so you can say, sir, margin is 2 epsilon. Okay, yes. Margin is 2 epsilon. Because it's a tube, no? So tube is like a cylinder. Okay, so it's a cylinder. So it's 2 epsilon. Or you can say the radius of the cylinder. That is the epsilon. Okay. So, and here is the height of the cylinder. Previously, we call it as hyperplane. Now we are saying it as height. See, what brain they have used. Now they are saying it as, okay, again, a height or the cylinder central line. We can make it as an epsilon tube, and that there will be a margin, and inside this, whatever be coming is good point, no error. Any point which is present inside, no error. And the goal is to capture as many as points. Same, see again. Here also the concept relies the same. Sir, we want to maximize the margin. Why? Because I want to increase the tube so that max of the point should be covered inside the tube. But there is one issue. If you increase the point, because height, this is a line, and this we call as regression line. This is regression line, same thing which we have in linear regression also. In linear regression also, no, we do have a line, regression line, and we were having the points above and below, and we calculate the errors. Okay, we calculate the errors there also, and we do perform MSC, mean square error. Same thing we do there also. Here, instead of just taking the errors, they are saying make a tube whose margin is 2 epsilon, and we need to increase the margin so that max of the point should be covered. But the issue is, if the width of the tube will be more, if the margin will be more, you can see, you can see. Let us suppose this is my tube, this is my regression line, and this point is very much far away from the regression line. But as per the concept, it says anything inside the tube is good point. It's not error, but you can still understand that how we can say that it's not an error. This is regression line and my point is present here. During test, okay, during test, my model will overfit. Okay, fine. My model will perform overfitting. Are you able to hear my voice? Am I audible?
Yes, sir. Now
Yes,
audible.
sir.
Hello? Am I audible?
Yes, sir.
Yes,
Yes.
sir.
Okay, fine. So, yeah. So I was explaining that in this case, we will be having an overfitting in the test. So there also in classification, we tried to maximize the margin, but our goal was not to maximize the errors. Okay, errors we don't want to increase. If there is misclassification there, and here if you are trying to gather the points inside the epsilon tube, but remember, you should not have error, high error. In this, if you are getting the errors, then reduce the margin. Okay, reduce the width of the epsilon tube. That's what you have to do. Okay, got it. Fine. Can you see my screen? Is my screen visible? Can you see my screen? Yes. Can you see my screen? Okay. So, yes, sir. Okay, fine. So, I'm teaching on this template. I'm moving this template. I hope you can see this template. All right. So, that is the concept of your epsilon tube and support vector regression. Let me start from here. Let me start it again. I introduce the topic. Okay, and all these things we are going to cover up here in support vector regression. So, support vector regression is actually a part of SVM. That's what I told. It's a part of support vector machine only, which is a supervised machine learning algorithm, which can perform both classification and regression. Classification we have seen. And the goal of the SVM is to train a model that assign new unseen objects into a particular category. That's what we do. Okay, that's what we do. Okay, we want to train our model and then we have to perform the prediction using this model. Okay, so linear support vector regression. Again, linear support vector regression. See the name linear. Just in classification also, na, we took the basic case. That was also linear. You are having a linear hyperplane. Here also we are taking the same thing. Linear support vector regression. Okay. In SVR, we use concept of epsilon tube, not the hyperplane. There is no hyperplane actually. Here we are having epsilon tube. But they are very smart people. They just changed the name hyperplane to epsilon tube. Okay. And we are having a regression line which has been passing from the middle of the epsilon tube. You have seen just now. The width, okay, what is epsilon? Epsilon is the width of the tube. I already shown you. Okay, measured vertically along the axis, not perpendicular to the tube but vertically, and this tube itself is called as epsilon insensitive. That means that any point inside this tube will be considered as error free. That will be considered as error free. The width of the epsilon insensitive tube is determined by the parameter epsilon. This parameter defines a region around the regression line where errors deviations are not penalized. I already told something which is considered something which is present inside the tube. Okay, all these points which are present inside the tube are error free. Okay, these all are error free. Something outside the tube, then we are having error. Okay, got it. So the width of the tube, they are saying it is 2 epsilon. That is the twice value of epsilon extending on both the sides of the regression line. So remember, this is our regression line. Okay, this is regression line. Okay, got it. Then what next it is saying? In SVR, data points that fall within this tube are considered as correctly predicted, not penalized. Data point falls outside the tube are subject to penalties. They are said to be deviated. And they are quantified by slack variables. I already introduced you. I already told you. Slack variable. Now, sir, what is the problem here then? The problem here is choosing appropriate value of epsilon. What should be the epsilon? Because you are saying the width is 2 epsilon. So what it should be? That will be like our optimization problem. Okay, larger the value of epsilon allows larger deviations from the regression line. If you increase the width, points will be present far away from the regression line. You will be considering them as correct, but at the testing case, you will be fail. Resulting in a wider tube and potentially a simple model. Simple model is an overfitted model. Remember, simple model. Okay, overfitting or underfitting. What it should be? It is underfitted actually. Simple model. Let's consider the case. Test case. A simple model is underfitted because more error. A complex model is overfitted. It is overfitted. We want a generalized model. Generalized model. Always remember these are the terms. Don't get confused. Simple model is underfitted. Complex model is overfitted. Generalized model is that's what we need. That is between simple and complex. If we narrow the tube, then okay, you are considering very less data points. Okay, if you narrow the tube, here if I explain, let us suppose let us suppose this is your regression line and only this much width you are making for the epsilon tube, only this much. There are many points which are present outside but you haven't captured. Then what to do? If you narrow, there will be very less points. If you more, then there will be more point. If you narrow, okay, the points will be present near to the regression line. But what about these? We are ignoring them. So they will not come under prediction. And if they will not come under the prediction, then okay, again you are having an issue. Okay, so conversely, a smaller value of epsilon leads to narrow tube, enforcing a stricter fit to the data. Strict fit. Strict. That means point will be very nearby to the regression line or present on the regression line. Then what to do? Here comes the choice of epsilon. That is based upon the characteristics of data and desired balance between model complexity and the accuracy. Again, we want to balance. We did perform balancing via lambda Lagrange multiplier in classification. And that was related to selecting data points only. What data points I should select as a support vector so that I can have a good hyperplane. Here also the approach. Okay, okay, problem changed, regression, but approach is SVM only. It is often determined through techniques like cross validation, where different values of epsilon are tried, evaluated on validation data to find one generalizes well over unseen data. Let's see what the things are going to be. In support vector regression, we are having slack variables to relax the strict margin and epsilon tube constraints. What these slack variables are? So slack variables allow for some degree of tolerance in fitting the data points within the epsilon insensitive tube and on the correct side of the margin. Like, like you can see in the diagram. Here it is. This is okay. Any point which is coming inside the epsilon tube is a good point. It doesn't matter whether they come over the regression line or whether they come away from the regression line. All are good, no error. But any point which is outside the epsilon tube, these are error points. Okay, these are error points. And okay, I told you that epsilon we took like this perpendicular. No, it's not. I just made this thing like it's not actually the perpendicular. You can see here that's parallel to the axis. This is epsilon and epsilon. This is 2 epsilon. Don't mention that okay it is perpendicular. I haven't made perpendicular. But in the diagram which I was explaining it was like this, but that's not been like a perpendicular thing. Here you can see how epsilon is been made. Okay, so 2 epsilon, here it is, and slack variables. Okay, above are slack, below are slack star. You can see this is slack star, this is also star. Again, above and below the tube. Above the tube slack, below the tube is slack dash, slack asterisk. Okay, so they told that in context of SVR, there are two types of slack variables: epsilon slack variables, epsilon and slack and slack dash. Slack for data points above the line, slack for data points below the line. Okay, or the tube, whatever you want to say, you can above the point and below the point. Okay, so these slack variables represent the deviation of individual data points from the margin. They quantify how much data point is allowed to be on present on the wrong side while still being penalized. How much? And remember one thing. These are the support vectors. Okay, let me again go to the diagram. These slack variables are support vectors. Try to understand the line what it told. It told that okay, we have to put penalty over them. These are errors, but these errors are supporting you, telling you that how much we can extend this epsilon tube. If we can extend this thing up to here, beyond that, beyond that, error will come. That will be a slack variable. Okay, that you will consider as a slack variable, and above and below the regression line. So from where the error starts, from where the error starts, you say now okay error got started till here, till here we can have an epsilon tube. From now onwards the error got started. So till here I am having epsilon tube because from this end the error got started, coming started. So these slack variables will be considered as support vectors here. Okay, let us understand the line again what they are saying. The slack variables represent the deviation of individual data point from the margin, how much far away these points are from the margin. From margin means epsilon sensitive tube. See, very very smart they are. In support vector classification, support vector regression, overall support vector machine. Okay, fine. Here we are having a hyperplane. Okay, here we are having it as epsilon tube. Okay, here we are having slack variables, like slack and slack dash. Here we don't have any slack variables. We are having the support vectors. Okay, these are also the support vectors. Okay, we do have a margin which you want to maximize. Here also the epsilon tube will be having 2 epsilon as a margin, which I want to extend. I want to maximize. But again, here also the same concept says that, okay, increase the margin, but do take care of errors. Here also I need to take care of the errors. So what the terminal, only the hyperplane, instead of hyperplane, it is having epsilon tube. Instead of having the support vectors for the class boundaries, we are having slack variables. Okay, rest we are having this 2 epsilon as a margin. Error, okay. Because it is regression, so there will be MSC. Because this is classification, so we are having accuracy. This is classification algorithm. This is regression algorithm. And if we do talk about regression correctly, as we are on discussion, so slack variables, they say how much they are deviated from the regression line, how much far away they are from the regression line. So that will be your error. Okay. And next, what they said, they quantify how much a data point is allowed to be on the wrong side. How much? Okay, well, this much is okay, or this much is okay, or this much is okay this side and this much is okay. What is, how much is okay? How much error you can afford? Remember one thing, there's a twist, sir. If there are many points outside, if there are many points outside, that means you are having a very narrow epsilon tube. And sir, if there are many points inside the tube, then sir, your model is simple, sir. Sir, what is this happening, sir? This is happening surely. Again, we have to find the optimal epsilon, optimal epsilon tube. We have to find this margin, because if we narrow, then also issue. If you wide, then also issue. It should be something optimal, so that I can have good number of points inside the margin, inside the epsilon tube. Okay, and for that only, they have also defined the constraints. Look at this equation. This is W square by 2 plus C into summation of slack plus slack dash. Again, this is objective function. Your same width margin. This is constraint equation. Okay, this is my constraint. C is a control parameter. There I was having lambda. Now they are smart again. They changed the terminology for it. Okay, so there we were having lambda. Now we are having C in this side. It is also controlling. This is also controlling. Okay, and what they said? What they said? They said C into summation slack plus slack dash. At that particular time, we were having hyperplane. Now we are having the slack variables. Slack variables will be responsible, and the slack variables will be greater than equal to 0. And these equations are defining, okay, above the regression line or below the regression line. These slack variables or data points are. So this will be actual predicted actual, the difference between them. So yp minus y is error na. So these are error points na. We have studied na in the regression, linear regression. So same thing they are writing, but in terms of slack. Anything above, anything below. I hope this makes a sense. Did you understood the regression or not? I started with this concept. Just please tell me. Okay, sir was present from the starting. Okay, all right. Okay, we do have few more things in this regression. Let me stop sharing it. Let me stop recording also.